Hello again. If you recall, last session we looked at whole insurance. So we looked at an insurance at age X, continuous case for a life that is for the whole life, forever. So this session will look at what if we are interested not for the whole life. What if you are interested up to this point? So we need to change this notation. We are interested is to give a benefit amount of $1 if death occurs here. And if death occurs here, we're going to give 0, right? So we are interested in this one. So if the person survives after age N, then 0. And this is what we call it term insurance, right? So we'll call it term insurance. And the term insurance, what we mean by it is, again, like it's a random variable z, is you get an amount of equal to 1 if death occurs, if our death occurs here less or equal to n. But if the person survives to age n or death is greater than n, we'll get 0. So we need to look at this random variable. So what is the actuarial present value? What is the actuarial present value? And the actuarial present value for this term insurance, remember it's the expected value of z. And we will give it a notation. It's called AX because it's the amount is payable at moment of death. $1, let's say this $1 is payable at time of death. So the $1 is payable at time of death. Whenever the death happens, the payment is made. It's continuous. We need to find the actuarial present value. Bring it here to X. What is the actuarial present value here for the dollar that is paid at the moment of death? And this is, we said it's AX, it's time, this is to say death occurs at or payment occurs at time of death, but it's not like the previous one. It's not whole life. We need to make it term to n, right? This angle n, it says term, and there is something else. We need to put $1 here. This 1 over x, superscript over x, is to say that the amount of money is paid only during the end terms. There is no payment made after that, right? So let's say again, what is this? What A tells us in actuarial science is insurance benefit. So we're evaluating insurance. N is the term. Payment is made over this term. Now this $1 here is 1 paid during N period, right? This one here is to say at time of death. So payment is made at time of death. Right? So let's write it again. So A, which is the expected value, or X angle N, there is a continuous case, which is the expected value of Z, as I mentioned. And what is Z for this payment is 1 and 0. So 1. So let's forget about 0, because if we take the expected value of the 0, it's 0 multiplied by any probability is 0. So let's focus on this one. This one is, and just to clarify also, this is not 1 actually here, because 1 at time of death, but the Z is the present value. If we take the present value here, so this one, the $1, we need to discount it back, the present value of the $1, it will be V raised to T, time of death, right? the v discounting factor, right? Or we can think of it is equal e minus lambda t, right? So we take now, because it's the expected value, and this is continuous case, so we take summation. Now the term is n, it's not to infinity, so n. Now we have e minus lambda, delta t, I keep saying lambda, delta t multiplied by f of t dt, right? So we can write it also e, again, term n, it ends in. The previous case, it was to infinity. Delta t tpx mu x plus t dt, right? It's very important to keep this one. If you want expected value of z to 2, or the second moment, the second moment actuarial mathematics, same as this one, so almost everything is the same. The only thing you add, similar to the whole life, you add just small 2 here. And this one will tell us the second moment. The 2 will tell us second moment. So same logic here, 0 to n, e, now minus t delta t, because now you raise it to 2, tpx ux plus t dt. This is mu tpx mu x plus t multiplied by dt, right? And the term here is important because this is term insurance, to say it's until n. Now, similar to what we did in previous session, we always interested in especially we are interested in uniform distribution. In uniform, if life is uniformly distributed, for uniform distribution, if life is uniformly distributed over, the life is over 0 to omega, so a x n 1 symbol is 1 over omega minus x. So omega is the limiting age, you subtract from it the age you evaluate it, multiplied by a bar. This is annuity certain, and last time it was omega minus x, now we do it in. If you want to do ax n, but you want the second moment, same thing, omega minus x a n, only for the term 2 of delta, right? So these, all of these, you need to memorize them, right? It's not very difficult. Now, what about exponential distribution? For exponential distribution with the mu is force of mortality, same logic. Now a bar x angle n payment is here. It's similar to what we did in the past. It will come mu over mu plus delta, now multiplied by 1 minus e raised to minus mu plus delta multiplied by n. Later on you will know the logic why we get this one, but it's very important to memorize also this one. If you want the second moment, it's simple. The second moment for the term insurance, all you need to do is the same, everything is the same, but delta becomes 2 delta. So same logic, mu plus 2 delta multiplied by 1 minus e minus mu plus 2 delta multiplied everything in the parenthesis multiplied by n, right? Very important to memorize also these things. There is a logic behind it. Later on, when we look at deferred insurance, we will know how we like where this comes from. But if you integrate, using the exponential distribution, it will come to the same logic. If you integrate the general formula here, this general formula, and replace TPX mu plus x plus t, you need to replace it multiplied by mu e minus mu plus lambda multiplied by t. If you will get this one, right? So these formulas you need to memorize them. Let's take a few examples here. Let's take example. Let's start with uniform. So let's take one is the x is uniform. So life at birth, x is uniform between 0 and 100. And delta here is 0.5. So we wanted to find the same logic here. Find AX1 for, let's say, for 10 years. Let's say the X is 30, let's make it. So for a life age 30, you need to find this one. So this is what we are looking at. Here we have 30 at time 40. So there is $1 here paid, the $1 is paid in this if death occurs anywhere here. So we need to look at this actuarial present value here. And this one we can right away calculate it from here. 1 over omega minus x, which is 1 omega minus x, 100 minus 30, which is 70, multiplied by a 10. You need to look at the difference between 70 and a 10. And this is 1 over 70. Let's write it here so we don't need this. So it will be 1 over 70 multiplied by 1e minus 10, which is 0.5 multiplied by 10 minus divided by 0.5. And if you do this, it should be 1,242. Right, it's simple. This is the annuity certain. I just applied the formula. You can, right? Now, what if you wanted to do A30 for the same uniform distribution, but the second moment of the term insurance for 10? Remember, I keep repeating this because I want you to practice this, how to read it. So A, the capital A, it tells us is insurance. There is a bar on top of it. What it tells us, it's continuous. Payment is made at time of death. Age 30, we evaluating it for an individual age 30. The angle 10 here, it tells us only the insurance covers only 10 years. So payment occurs here. What's missing here, we need to have 1 here. And the 2 here, it tells us is second moment, right? So this one, we can use the same logic, 0.70, a 10, but all we need to do is to use now delta. Instead of it was 5%, we need to use it 10%. So it becomes 1 over 70, exactly the same logic here. It's 1 e minus 0, 1 multiplied by 10 divided by 0, 10. If you do this, should get you 0.9. 0.33. What if you wanted to find variance? It will be 0.9033 minus this one raised to 2. 0.11242. And this should be now 0.777, right? This is straightforward. There is nothing complicated here. If you know the formula, it's easy to do it. You might be overwhelmed again with these terms. So many notations here. There is a logic behind it. If you just follow the logic, you will be able to read all these notations easily. It's nothing complicated. just the logic, and the more you practice. And this is related to this. Next session I will put I will have one more session, then I'll put a very large a problem set that helps you to do problems. So the problem set, you need to do them, so it helps you to practice, because I cannot spend a lot of time doing so many problems. In the live sessions we will if you have any question related to those problem sets, you can tell me. Now let's take another example for the exponential distribution. Now let's look at exponential distribution here. Now let's say the random variable is x is uniformly distributed, x is not uniformly, is exponentially distributed with mu equal, let's make it 10% or 0.5%, and you have delta is, let's have delta is 10%, similar to the same question we did before. But now we don't want whole life insurance. We want the question ask you a bar 30 for 10, and there is 1 here. How we read it? It's insurance for a life age 30 to pay $1 for the next to pay $1 if death occurs within the next 10 years. So if death occurs at moment of death, there is a payment of $1. How to evaluate this one? This is simple. We look at the formula here. We already have the formula here, right? And we apply it. We plug in. It's similar to the life insurance, which is mu over, so 0.5 over mu a plus delta, which is 10%, now multiplied. So up to here, this is like the AX. But now we need to multiply by 1 minus, now we look at it, e to minus delta plus mu, e minus delta plus mu, which is 0.5 plus 0.1 multiplied by 10. Right. This is simple, right? You follow this logic. And if this one is now 1/3 multiplied by this, so if you calculate this one here, is usually if I'm rushing, all you need to do, that's the beautiful thing about like these sessions, that you can stop me, do your calculation, and then like you pause me, and then you do your calculation, and then you verify your calculation. That's the best thing to do. So if you stop me and you did the calculation, now it will be, this one is 0.259. And similar, if you do the second moment, it will be 0.5. Now 0.5, you add to it, instead of 1, it will be 0.2, because it's 2 delta. The difference between this and this is 2 delta. Yeah, just right. And then multiplied by 1 e minus 0.5 plus now 0.2, right? Do you see the difference here? And why 0.2? It's because it's 0.2 multiplied by delta, and then 10. It's the formula, it's here, right? Should be easy. And if you do this, now we will get this one to be equal to, again, you pause me and you calculate and verify your answer. So now if you calculate, the variance of z will be 2ax, sorry, and this is, we already calculated it, minus 259 -259 and what I got is 0.1165. Right. Simple. If you just know the formula, and then you quickly can apply it. Again, don't be overwhelmed. These formulas are not much. The more you practice, the easier they become. They become very natural to you. So there's really not much of, it looks hard, but it's not. The more you practice, they are easy. Not much of hard math, but it's the difficulty of, remembering all these notations. And there is logic for the notation. So let's continue our logic for the notation. Now we will look at another term. It's called the pure endowment. Pure endowment insurance. Now somebody age X here, and then they have X plus N. In the previous term insurance, we said if death occurs here, you get money. But here, payment is made if you survive. Payment is made if you survive, and then we need to get it back here. So the payment is made if you survive. So the random variable here is, now it's the present value. Remember, the present value is the random variable. This $1, we get it back. So it will be E minus, or we can use VN. Look, sorry, maybe we should have 0 first. 0 if death occurs, T, if a death occurs less than N, less or equal to N, you get 0, right? But if death occurs greater than N, then you get this one will be the discounted value of the $1. The discounted value of $1, the present value, you can write it V to N. Right, it's simple. This is called the pure endowment. So pure endowment is conditional on surviving, not on death like the one before. So now we need, and we can call this one Z. What is the expected value of this Z? So Z is again the present value. And now what's the actuarial present value? So the actuarial present value need to include the probability. So what's the expected value of Vn, which is again expected value of Vn? You can write it also this one, E minus delta N. Right? And the notation for this one is, in actuarial math, it has two notations. The first notation, as you would expect, is A, because we look at benefit amount for somebody age X, because we're evaluating at age X here. And now we have until N. There is a term, but the payment is not here. The payment, just to differentiate between, if it's here, then we're looking at term insurance. But here is a pure, the 1 will be over N. So what you would recognize here is first that you don't have bar. There is no bar here. For this one, what does it mean that there is no bar? It's discrete. One. Second, what you can see is, or you don't see, but no need for integration, because it follows that's discrete, no need for integration. It's discrete, no need for integration, right? And the difference between this one and this one is triggered by survival. The one before, it was triggered by death. The payment was triggered by death. Here the payment is triggered by survival. When payment's triggered by survival, the one here goes, or 1 if you survive age N. 1, it say that, the dollar is paid here, right? So it's over the N. Here it's paid to the left, right? See how we read it? There is no bar. So what is AXN? No integration here, no need for integrations. Expected value, it's simple. What is payment is paid if you survive. The probability of survival, which is PX, so N, PX, an individual, small letter here. an individual xn to survive to n, then multiplied by vn. You can write it also npx multiplied by e minus delta n, right? Want you now also to look at this relationship. It's very, very important. Why? Because this is recall how we started last session, or when we started about insurance benefit. We said if you have $1 here certain, if this is certain here, it becomes present value. But if it's not certain, this $1 is conditional on survival. To get it here, we need the actuarial present value. So this one is, because it's very important concept, it's the actuarial present value or the actuarial discounting rate. This is the discounting rate, here is VT, VN I mean. Right? It's 1 over 1 plus I to N. Right? But the actuarial present value, you include the probability. Because this one is very important like that. It's because this one is the actuarial present value. So because it has another term we use, it's NEX. So NEX, it's also the actuarial discounting factor, which can be written AX N here, which is equal to probability of X to survive to N multiplied by Vn. And this capital E is to say this is the discounting factor, but actuarial discounting factor, not only present value, but actually the actuarial present value. It's very important concept. Now, we looked at this first term. What about if you want to calculate the second term? Let me write it here, right? What if you wanted 2AXN? It's simple. This is NPX V2N. Can write it NPX, the survival, multiplied by E and then, right? You can also remember it this way. Now, how you calculate variance? And remember what is Z. Payment is paid at if the person survives to year end. There are two ways: 2AXN minus AXN. Alternatively, variance of Z. Remember, it's Z, it's 0 or a value, 0 or a value. We define it here, 0 or a value. This is because this is in probability theory, this is similar to binomial distribution, Bernoulli distribution, right? In Bernoulli distribution, instead of $1 if an event happens, this is an amount if an event happens. So the amount is if an event happens is simply you can write it. This distribution is simply you can say Px and Nqx, right? So probability to survive, probability of death, and multiplied by V2N, right? So this another way, two ways you can calculate it. One is the probability to survive multiplied by probability for death. Probability to survive multiplied by probability of death multiplied by value. This is, if you remember, Bernoulli distribution, because it satisfies the Bernoulli distribution, so we can use this this relationship, right? Let's take example on this one. Now let's say let's take uniform. X is uniform over 0 and 100. Let's say delta is 0.5. The question is, we wanted to find A30, the $1 here. We don't need bar because it's this discrete distribution. So this is a payment of $1 paid if the life at age 30 survive to age 40, 30, 40. If the person survive to 40, then we'll get $1. What's the actuarial present value? So the actuarial present value for this one, it's straightforward, right? A30, then 1 is, we need to multiply like V, or because we have delta, let's E minus 0.5 multiply by 10. Then we need the probability to survive. What's payment multiplied by probability to survive? What is the probability of now TP40? Sorry, 30. For a life age 30, what's the probability to survive 10? But it's uniform distribution. So TP30, because it's uniform distribution, is actually, let's have the general form. TPX for uniform distribution, and you have from 0 to omega, will be omega minus X, right, minus T divided by omega minus X. So omega, but so this just like recall, by now we should know it. So TP30, when omega is 100, if you apply this one, then it will be 100 minus 30, 70 minus T, which is 10, divided by 70 minus 30, 100 minus 30, it will be 70, so it will be 6 over 7. Now we take this one and we compute what is the result. If you do that, A minus 0.5 multiplied by 6 divided by 7. What I got 51%, or 0.5199, right? This is what I got. What if you wanted to compute AX, let's say 30, 10, 1. So the second moment, what is the second moment? The same, we go to the formula. This is the formula. NPX multiply O. I realized there is a little error here. Sorry, a little error here. The two, this one should be 2 delta N. Sorry for that, 2, because this is the second moment. If you notice that, go back to the formula for the second moment, it should be 2 delta. But I would imagine, you know, like you already figured out this typo while you're writing, because the same logic here. You double the force, right? So now we go back to this formula here. So it's NP, let me write it here, NPX multiplied by E minus 2 delta N, right? So NPX, or 10P30 multiplied by E 0, let's write it here, 2 multiplied by 0.5 multiplied by 10. 10P30, we already calculated it here, it's 6 over 7. Now E, instead of saying what our delta was 0.5, right? So 2, it will be minus 1, right? times 6, then divided by 7, I got 3153. Now, what if you want to calculate the variance of C? As I said, there are two ways. The first way is you T-A-X minus A30 10 T2. This is one way, and this will be 0.3153 minus whatever we got here, 5199. Let's do that. I have it saved on my calculator because I just did the calculation. So minus, when you have it saved in your calculator is good, because you can just calculate it. So what you would get here is 0.45, right? And now this is one way. Now let's verify if the other way works. Let's verify it. So this is one way. The other way, if you remember, this is Bernoulli distribution. All you need to do is to say probability and its complement. So NPX, or let me write it, 10P30 multiplied by 10Q30, the probability and its complement. They add up to 1, but we need to multiply them. And then we multiply them by A minus 2 delta N. Right, and this is just where we got this one from. It's just to remind you, this is a formula I told you here. V2N, which is E minus, because we are given lambda. If we are given I, then we better use that one. If this is 6 over 7, this is the complement of it, 1 over 7. And this is E minus 2 delta 210 multiplied by 0.5 will be 1. Let's see if I get the same answer. Now, minus 1, enter, multiply by 6, enter, divided by 7. Seems I got a little mistake. Where is that? Divided by another 7, sorry. Divided by 49, I didn't. Yeah, now I forgot divided by 49, I divided by 7. But it's actually, you have 2 7, 49, so you should get 0.45. But the same answer. The very same answer. Now, for exponential, distribution, AX, for AXN, the pure endowment for exponential, which is also NEX, is equal to E minus lambda n multiplied by, again, the payment or the present value multiplied by the probability to survive. Probability to survive in an exponential distribution will be this. So for exponential distribution, it will be E lambda plus mu to n. Right? So NEX. This is very important relationship. It's very important. So it's delta plus mu, force of interest, plus force of mortality multiplied by the n, the period. So this is the discounting factor, the actuarial discounting factor for exponential distribution. Similar, if you want, the second moment will be all the same all the same, but 2 delta plus mu multiplied by n, right? Not much here, not much. So let's recall what we did today. We did a few things today. We did, one is term insurance. Term insurance, we call it AX, and this continuous case, $1 here. Then we looked at the pure endowment, and this one is AX. There is no bar because it's discrete, and then we have N, and the payment is here. Payment if the person survive. What if we add these two things together? If we add these two things together, we will get a term that is called, now this term is called endowment insurance. And endowment insurance, see the difference. The first one is term, the second one is pure, which is equal to term insurance plus a pure endowment. So endowment insurance, and then term for endowment insurance, it will look like this: A X N for the continuous case. So how we read this one? This is A, it tells us insurance, bar it's payable at time of death because it's continuous, for an N period. It's not for whole life, it's for N period because the angle. We don't see anyone. And that's where it becomes interesting. So if the individual dies within N years, we'll get $1. If the individual dies after N, survives N years, we'll get $1. So if we try to see this one, it will be AX, as I mentioned, N1 here. So term insurance plus AX N here. So if this is, let's look at this one. If this is now pays $1, the present value Z here for this one will be VT, also VT. That's quite interesting here. VN here. So let me visualize it here. Z here X plus N. Now if $1 here happens at time of death, if $1 here, we'll take it here at time of death. So time of death is T, then we have VT. So if T is less or equal to N, we have VT. But if death happens here, then whenever, like as long as you survive, you have $1. You discount it back, VN. So if T is greater than N. And you can see that this one will give you this one here. This one will give you this one. And this one will give you this one, right? So let's summarize it. AX N continuous is equal to AX continuous 1 at time of death plus $1 if the individual, oh sorry, we don't have a bar here, if the individual survive to N years. Can be also written as AX So the calculation for this one is you use just this. So if you question, you will need to calculate this one. You calculate one and this one, right? So you can add them up. So there is not much of calculation for this one. Let's take one example. Now let's say that x is uniform, and remember x is remaining lifetime at birth. It's uniform over 0 and 100, the same equation we've taken it so far, and delta is 0, 5. So now recall, if you go back to your note, you will see that ax, oh sorry, we said 30, we find it to be 0, 1, 1, 2, 4, 2, and then we find 10 E30, which is A30, 10. We found it to be also 0, 5, 5, 1, 9, 9. Then A30, 10, and what you see, there is no one here. There is no one here. Is equal to 0.11242 plus 0.5199. So the endowment insurance will cost 6323, right? So not much of calculation for this one. So I used here uniform distribution and only uniform distribution and exponential, just to explain these condition. Let's say you're not having exponential or any other things, then you use the integration one by one. So you take the formula, you integrate it, and then you sort it out. What we will do, we'll introduce another few things next session, and then after that you will have a long problem set that you can solve it. I will also solve a few other problems when we finish this whole chapter. Okay.